Hello, my name is Mira Kuchibuza Marcel, and I'm the founder and the director of the Pan African Citizen Science e-Laboratory. So, today we are going to be exploring the universe through the cosmic messengers. The universe through the cosmic messengers. So, you're going to understand what cosmic messengers are. So, by the way, a couple of months ago, we have been exploring the International Space Station. We explored what is International Space Station, and also we explored satellites, spacecraft, and the space station, and we talked about what makes them different from one another. So, like for instance, we say that the satellite is like a camera you put in space to be observing Earth or to be observing the universe. Then we say a spacecraft is like a vehicle that conveys astronaut or equipment from one location to another, for instance, from Earth to the Moon or from Earth to the International Space Station. And then we have space station, which is like a house or a combination of a house and a laboratory for astronauts to live and perform experiments. So we also explore why humans built the International Space Station, or should I say, why the International Space Station is necessary. We explored it because there are some experiments you can perform on Earth, and and you cannot replicate them in space. Okay, they are possible. They are impossible. There are some experiments that are impossible on Earth, but as possible in space. If you remove these effects of gravity on the experiment, you see a lot of interesting things happening. So we explore that. That's why we build the International Space Station, so that we can perform experiments, most especially medical experiments, biological experiments. And then we explore the major space stations that have existed so far. We explore the Salyut 1, that is the first space station. We explore the Skylab. We explore the Mir. We explore the International Space Station. We explore the Chinese space station Tiangong, and so on and so forth. Okay. So today, as a table of content, we are going to be. I'm going to introduce Cosmic Messenger to you. So, and it's gonna be a very long lecture. It's gonna be a series of lectures. It's gonna cut across months. Okay. So, the first thing I'm going to talk about is the introduction to astronomy and cosmic messengers. I talk about how astronomers study objects they cannot visit, and then I'll talk about what is cosmic messenger. I'll talk about the history of the discovery of cosmic messengers, and then invention of the optical telescope. Talk about multi-wavelength astronomy. Talk about multi-messenger astronomy, and why are multiple messengers necessary. So let me just summarize what I just talked about now. So I'm not going to be going deeper into these cosmic messengers. I'm just going to introduce cosmic messengers and then go into the history of how we came about discovering them and why they're even necessary. Okay, so take note of that. So, by the way, this lecture is sponsored by the Free Astro Science Group. So, introduction to astronomy and cosmic messengers. So, let us start from what is astronomy? Let us start with that. What is astronomy? Astronomy is a scientific study of celestial objects, space, and the universe as a whole. So, astronomy seeks to answer fundamental questions such as what are stars made of? What are stars made of? If you look at a star, what is it made of? So, that is one of the questions astronomy seeks to answer. What are planets? How are planets formed? Planets around our sun or planets around other stars. How are they formed? What are black holes? How did the universe begin? Okay, and what is dark matter and dark energy, and are we alone in the universe? So these are some of the many questions that astronomy seeks to provide answers to. Okay, so However, unlike many other science field of science, okay, which are experimentally based, astronomy is primarily an observational science. Because if you talk about stars, you cannot bring stars to your laboratory to experiment with. You can't even go take the sample. It's not possible because of distances. Okay, you can't bring galaxies to your laboratory, to your lab table. You can't bring black holes, okay, into the lab. Unlike other field of sciences, they can go on a field trip, get samples, and come to the lab to experiment. Okay, they can have a controlled experiment. So instead, astronomers rely on information that naturally travel through these distant objects to Earth. So for instance, like what I've just said, astronomy versus experimental science. So we have physics. It's physics. So physics would test theories using experiments in the laboratory. Okay, although astronomy is part of sorry, yes, astronomy is part of physics. Okay, but in the higher level, it diverges. Okay, it diverges. But when I talk about physics, I talk about like experimental physics. That some physics is performed in the lab, like material science, material physics, or solid state, or nanoparticle physics. Solar physics. All of these things you can experiment in the lab. Okay, so we have chemistry. You mix substances and observe the reaction. Do you understand? In the laboratory, these are experimental sciences. You have biology, you study living organisms and observe their processes. So you have medicine, you test treatments, understand diseases. You have engineering, even engineering, you design, you build, you test, you improve upon the solutions that you've built. Then we have environmental sciences too, climate change. All of these things are within us, are within our reach, so we can reach out to them and get samples and come to the laboratory. But astronomy is not like that. We can't go to the moon. It's expensive, although humans have started doing that. But it is not like you can just go to the moon. You can just get a grant from a sponsor and go to the moon. It was practically impossible. It takes a lot. It takes a lot. Okay, even if you can't go to the moon, you can go to stars. You can go to galaxies. You can go to black holes. You can bring them into your laboratory. So we naturally depend on signals or information coming or emanating from these objects for us to make our deductions about them. So if we cannot have those things in the laboratory, if we cannot reach them, how then do astronomers study objects they cannot visit? Does it make any sense? You are studying something you cannot visit. I've been to a hospital before, and the doctor asked me, "What did you study?" I said, "I studied astronomy." What does that mean? He asked me. I said, "It means studying the space, studying stars, studying objects in the universe." So he said, because of his background, he was like, "Okay, do you go to the moon to pick samples? How do you do it?" So I told him, "No, we depend on electromagnetic waves and signals from this object to do that." So I don't know if what I said made sense to him, but that is it. So how do astronomers study objects that they cannot visit? Make it make sense. So how do we do it? So and how I'm going to start is by letting you to imagine trying to understand a person who lives thousands of kilometers away from you without ever meeting them. So you imagine how you do that. So how do you do that? So the only way you could be able to do that is through sending them messages such as letters. You can send them a letter, you can write them a love letter or whatever letter. Okay, this is how you reach them. Okay, so you probably will send them a letter, or they send you a letter. Okay, at least that's a communication. Then you can call them through phone, which is electromagnetic waves, okay, through phones. You can email them. You can have or you can communicate to them using videos. Like you can even use Zoom, to interact with them, video calls. Okay, so however, what I want to point out is this: each type of the message in this four that I've just listed reveals different information. It reveals different information. For instance, if you are writing to someone, it reveals a different information from having a video call. Do you understand? So astronomy works in much the same way. It works in much the same way. So most astronomical objects, like I said before, are far beyond our reach. For instance, you look at the moon is about 384,400 kilometers away from Earth, from us. Okay, if you talk about the sun is about 150 million kilometers away from us, and even the nearest star system to the sun, we call it Proxima Centauri, is a system of 3 stars. Okay, so they are located at a distance of about 4.24 light years away. You know what that means? Light year? Light year is how far the light, a beam of light travels in 1 year. You know, light is the fastest, okay? So imagine the speed of light, okay? Then you times it by, okay, in 1 second, light travels to light. Okay, the speed of light is about 3 times 10 raised to power 8 meters per second. That means every second it travels a distance of about 3 times 10 raised to power 8, right? That is about 300 million meters in 1 second. So check how many seconds are in a year. So if you can do the conversion and multiply it, so the distance the light travels in 1 year gives you a light year. So if light travels in 3 times 10 raised to power, 300 million meters per second in 1 second, that means 1 light year is a lot of distance. Okay, it's a lot of distance. Okay, so then think about 4.24 light years away. So that's a lot of distance. So look at the sun here. Look at the Oort cloud. You know the position of the Oort cloud. Then you have 2 light years, 4 light years. So Proxima Centauri is a system of 3 stars. They are at 4.24 light years away. Or even the nearest galaxy to us, called the Andromeda Galaxy, which is located at a distance of about 2.5 million light years away. So look at that. So how do we study things like this? As scientists, how do we study things like this? So that is exactly what I'm diving into. So because of these enormous distances, we cannot directly sample or visit most celestial objects. Instead, they send us natural signals that carry information across space. These signals are known as cosmic messengers. I hope you understand where the idea of cosmic messenger is coming from. Okay, cosmic messengers are these signals that this object emit. Signals, information that they emit from their body. Okay, so we depend on them. All other things we know about the universe are signals, those natural signals that we have received from them. So, and the question is now, what is a cosmic messenger? What is a cosmic messenger? A cosmic messenger is any form of information or particle that travels through space from an astronomical source and carries information about its origin. So by detecting and analyzing these messengers, astronomers can determine what they are. From there we can know if they are stars or if they are planets or the moon or comets or asteroids or nebulae, star clusters. So you see that most of the things you know in astronomy comes from light emanating from these objects. Okay, we can know even their location using the celestial sphere. We can know their location. We can measure their temperatures. For instance, if you look at the star with a telescope and it's looking reddish, probably a low mass star. If you look at those ones that are massive, they are looking bluish, you know it's a high mass star. So we can study the temperature. So from there you can even deduce the temperature. Okay? You can study their chemical compositions, what they are made of. Okay? You can study their mass and their motions. You can study their mass and their motions. So you study the magnetic fields surrounding them. We can study their internal structures. We can even study some violent events like a supernova explosion and effect it has on the environment. Okay? So you can see this exploding and it has effect on its environment, like you can see it in the picture. So by detecting and analyzing these signals, we can review all of these details. So you see, everything we know about astronomy is coming from these signals. So today, astronomers recognize four primary cosmic messengers. We have four. We have electromagnetic waves. It's a wave. It's a transverse wave between electric fields and magnetic fields. Okay, electric fields oscillating at 90 degrees angle to the magnetic field and vice versa. So the electric field, the change in electric field gives rise to magnetic field. So the idea is is a deep physics principle. So that is electromagnetic waves. So that is number one. We have gravitational waves, an interesting kind of waves. A lot of people have not known this kind of wave because you cannot see it with your eyes, of course. The only kind of wave you can ever see is the electromagnetic waves, but you cannot see this one with your eyes. But with some detectors, you can detect them. Okay, so with that we have neutrinos. These are invisible particles. By the time I'm done with this lecture, you're gonna understand that most part of the universe are invisible from our eyes. Most part of the universe are invisible from our eyes. Then we have cosmic rays. We have cosmic rays. Okay, we have cosmic rays. So each of these messenger provides unique information that the other cannot provide. So I'm going to be, in my next lecture, I'm going to be delving deeper into each of them one after the other. I told you this is going to be a very long series of lectures. So I'm going to be delving deeper into each of them in the coming months. Okay, each lecture I'm going to be treating this one. Depending if I finish it, I'll move to the next one. Okay, so but for now, I want to talk about the history of the discovery of these cosmic messengers. How did we get here? Like I mentioned before, I mentioned the electromagnetic waves, mentioned gravitational waves, I mentioned neutrinos and gamma rays. So how did we come about discovering them? So that is about the history of the discovery of messengers. Since evolution of human, for thousands of years, we have been looking at the night sky with our naked eyes. Okay, the naked eyes. With our naked eyes, we can see the sun. At least at sunset and sunrise, you can see the sun. Oh, there's the sun there. You cannot see it during the daytime because it's gonna blow your eyes. So you look at it during sunset and sunrise. You can look at the sun. So with our eyes, we have been observing the moon and the planets for thousands of years, thousands of human history. We have bright stars. Look at the bright stars. Like if you look at the Milky Way, some countries this is pretty much visible. We have seen the comets. We've seen meteors. We see none of these things happen. However, we cannot. We have. Wait. This we have recorded. Ancient astronomers have seen this and recorded these events, but they can't really interpret. They can't zoom in on this to know details. So they came up with a lot of mystical things. Okay. Okay. So observation with the naked eyes has limitations. Okay, it has limitation because you can't see far, you can see deep and far, and there is more you can see, and that led to the invention of the optical telescope. Mind you, this whole thing talked about our optical spectrum, under optical spectrum. Okay, so but we now invented a tool called an optical telescope we can use to magnify optical light. Do you understand? So it was invented, the optical telescope was invented by Galileo Galilei in 1609. So, and that revolutionized astronomy. So optical astronomy collect visible light, allowing astronomers to discover more things. So that is Galileo Galilei. That's his picture. He did a great job. Okay. So from there, with this telescope, we're able to, okay, like Galileo, when he invented it, was able to look closely at the moon, and he saw mountains on the moon. Although this is not the picture he saw, but this is just later pictures. But he was able to see mountains of the moon with his telescope, and that was amazing. He was able to see sunspots. He was able to see the four largest moons of Jupiter. This you cannot see them with your naked eyes. Okay, we start. So imagine that you have moon on Earth, and then with this telescope, you now see that other planet like Jupiter have moons. So that is mind-boggling. It's going to change your perception about life, about reality. So it kind of changed things. You can see phases of Venus. This is Venus. You can see phases. He was able to see the phases. Although this is not the image, the data he collected. Okay, this is from, you can easily see these things on the internet. Okay, I'm just pointing out the things he was able to use this telescope to observe, and he was able to see countless of stars, invisible to the naked eyes. Okay. So, however, even this optical telescope posed some limitations. Remember, I started with the naked eyes. Human beings started observing the night sky with the naked eyes, okay? And there was a limitation because of our eyes, we cannot see deep and far. And then we invented the optical telescope too that helped to magnify things. Even upon that, there were limitations. So let me point one of those limitations. Visible light represent only a tiny fraction of the information available in the universe. Okay? So for instance, many objects you have around you emit light in different spectrum, not just visible light. This is a wonderful discovery. Like if you're looking at an object right now, you are looking at it in optical spectrum. But that same object is emitting light in other spectrum that we didn't know before that existed. Okay, so, and for instance, if you're in a house demarcated by walls, okay, if you look through the wall, you can't see what the next person is doing. But with some electromagnetic spectrum tools, you can see the next person. Okay, you can see the next person because they emit other forms of light apart from the visible light. Okay, so these are some of the limitations of observing the universe in the visible spectrum using optical light. So look at this person. This person, as you're looking at this person, you're looking at him in the visible spectrum. I mean the optical spectrum. Okay, as you're looking at him, so he's putting his hand in his bag, in this nylon bag or whatever. So you cannot see his hands. That is that is in optical spectrum. But if you observe him in the infrared spectrum, you're gonna see his hands. In fact, you're not gonna see those block, this nylon block, that is the blockade that is blocking his hands. That's exactly what I'm saying. So we started discovering that in the 20th century. So scientists started realizing that objects emit radiation across the entire electromagnetic spectrum, not just on visible light. And what are those electromagnetic spectrum? The first, I'm going to call them out. I'm going to mention them according to their increase in frequency. So we have number one, we have radio waves. The number two, we have microwaves. Although microwaves and radio waves are, like we say, microwaves are higher frequency of radio waves. Okay, but we have that. Then we have visible light. So we have infrared. We have infrared. Then we have visible light or optical spectrum of optical spectrum. Then we have UV light. That is 5 now. Then we have X-rays and we have gamma ray. Those are the 7. We have 7 of them, 7 electromagnetic spectrum. So as you are looking at an object, okay, any object emits all of these. Okay, any object emits all of these. So it depends on what you observe it with. So that is the idea of the black body that was being talked about in the 20th century. So for instance, look at the sun. Let us use the sun for as an example. The sun emits light in radio waves, and that is how it looks. So if you have the eyes that is sensitive to the radio waves, you're going to see this. Or you have a tool that is sensitive to the radio waves, you're going to see this. If you have a tool sensitive for the infrared, you're going to see the sun like this. And this is the way we see the sun with our optical telescope, or even when you look at it during the sunset and sunrise. So that is the visible. And here is the sun in the UV light, and that's the wavelength there. And here is the sun in the X-ray and sun in gamma ray. So you see the sun emits. So you can see that we have different kinds of spectrum apart from optical light. Okay. So let me give you another example. Like this is the Helix Nebulae. This is the Helix Nebulae in the infrared spectrum, and here's the Helix Nebulae in the visible spectrum, and here's the Helix Nebulae in the ultraviolet spectrum. Just different kinds of information, and they are all unique. They give unique details. Okay. And we also have the Pillar of Creation. We call it the Eagle Nebulae. The Eagle Nebulae. This is the Eagle Nebulae in the visible spectrum, and this is the Eagle Nebulae in the infrared. So different details revealed by this electromagnetic spectrum. So remember, this is multi-wavelength astronomy. I didn't mention it, so that is multi-wavelength astronomy. I have just mentioned all the electromagnetic waves. So even upon the advances we have made in the electromagnetic waves, we see observe there are limitations with them. There are some limitations. I'm going to mention some of the limitations. So, some objects emit little or no electromagnetic waves in the universe. There are some objects that do not do that. But for instance, look at the content of the universe as we have known it today. We have ordinary matter. Ordinary matter are just like the stars, galaxies, everything you can see under the EM waves, the 7 EM waves. Okay? Those stars, galaxies, black holes, they all make up just 5% of what we can see. So what happened to the 95%? Okay, from there you have dark matter, which takes up 25%. Dark matter are matter that we cannot see. They do not interact with normal matter. Okay? We cannot see them. So how do we detect them? Okay, how did we even detect them? That will come back when I talk about gravitational waves or gravitational force. Then we have dark energy. Dark energy is a form of energy that has taken up about 68% of the universe. So you see, so much of the universe is invisible for us. We cannot see much of the universe. So we only see 5%. 5%. Think about that. 5%. Upon all these discoveries we've made, we've discovered we have 2 trillion galaxies in the universe. We have countless stars. We have planets. And I'm telling you, all of these things are just 5% of the universe because we discovered them using electromagnetic waves. They are emitting electromagnetic waves and we see them. Okay? So black holes, what we call isolated black holes. Black holes are strange objects that do not emit light. They suck in things. Their gravity is so high that they do not, nothing escapes them. Okay, so they suck light in. They suck anything that is suckable around them. So they can eat up anything that is surrounding them. So they might even become isolated. Okay, so how do we know that they are there if they are not emitting anything? I mean, they are not emitting anything. So how do we know? So these are some of the limitations of the electromagnetic spectrum. We also have planets we call rogue planets. Rogue planets are planets that have detached from their whole stars due to some catastrophic event like supernova explosions. Okay, or maybe it could be collisions with the bigger other rogue planets. Okay, so they are just roaming around the universe. So although those kind of planets can emit or infrared, but due to their size, no matter how big a planet is, if you compare to the size of the universe, it's insignificant. So even if this planet is 1 light years away from us, we may not be able to see it in infrared because of how small it's going to be. Okay, so and some of them might even have moons and we not even know. How about interiors of stars? Interiors of stars. Interiors of stars, the core, like stars, like the sun has a core. Okay, and this core traps light because the lights that we see from the sun that makes the day are trapped in the core of the stars, and it takes millions of years for it to come out. To make it to the surface, it takes millions of years. Okay, so and when it makes it, we don't know what is going on in the core of stars or the sun. So we are blind to these events if we depend only on electromagnetic waves. We also have the universe. Now look at the universe. The Big Bang doing the formation of the universe. We have hydrogen. Okay, there was an immediate nuclear fusion that gave rise to helium. Okay, so what I'm saying is that from that hydrogen and helium, they started collapsing. They were collapsing in birthing stars. From stars, we have galaxies. Stars are element factories. So stars, we are producing these heavy elements. So when they explode, it disperses heavier element into the intermolecular molecular medium, and heavy elements there, and some of them form planets. So what I'm saying is that not all these hydrogen form stars. I mean, 90% of the universe is still in their natural state when they were birthed. Okay, when they were birthed, like hydrogen and helium, I mean, a huge percentage of the universe is still in this helium and nitrogen. So how do we see them? How do we see this? How do we see them? So how do we see them? So some of these hydrogen, some of the hydrogen are ionized. Okay, they're ionized. So when they are ionized or excited, when they fall back to their ground state, they emit radiation. what we call 21 centimeter line, so we can see them. Okay, then we also have but not all of them are ionized. We have some that are also in molecular form, molecular hydrogen. Okay, they do not emit anything, just and also neutral hydrogen. They do not emit anything. So if they don't emit anything, how are we supposed to detect them or map them in the universe? So it becomes incredibly hard. So the only one we can detect is the 21 centimeter line I talked about by excited hydrogen. How about helium? Helium can be neutral, like inert helium, and then we have ionized. So we can also detect ionized helium. So what I'm saying is that those hydrogen that form molecules H2, okay, we call them cold molecular hydrogen. Okay, they are the most abundant molecules in the universe, and we cannot detect them. So I'm just showing you some of the limitations of observing the universe, depending on the electromagnetic spectrum to understand the universe. And then we have stars. Stars that are formed in dense molecular cloud. So this dust or gas cover them. Okay, they cover them, obscure. So light, even if light is emitted from the stars, they absorb the light. Yes, it gets them excited, but they are huge, so the light doesn't even make it to the end. So we don't even know. So we have a lot of these gas and dust covering stars, so we cannot even see what's going on inside the stars, going inside the interior of those molecular those hideouts. So we need other kinds of messengers for us to see what's going on inside. Okay, so we have some cosmic events that produce signals beyond the electromagnetic waves. So that requires other types of messengers. So that will land us to multi-messenger astronomy. Remember how this is going. We started from optical light with naked eyes, and then we invented optical telescope, and there were limitations. So we now discover the multi wavelength messenger, which is the 7 electromagnetic waves. So for that, we also saw there are limitations, and now we have multi messengers. So I want you to follow the steps. So modern astronomy has 4 cosmic messengers, like I've pointed out before. So we have electromagnetic waves, which review mostly temperatures, composition, and emitted radiation of celestial objects. So we have gravitational waves, which review motion of massive objects and distortion of space-time. We have neutrino, which escapes from dense interiors like stars. So from neutrinos, we can know what's going on in stars, providing information about nuclear reactions and extreme environments. We also have cosmic rays or particles, which review how matter accelerates particles to enormous energies. So by combining these observations, astronomers can obtain a more complete picture of the universe than any single messenger can provide. So now, why are multiple messengers necessary? You can answer that, okay? Because no single messenger can answer every astronomical question. Each has strengths and limitations. For instance, we have black holes. Black holes don't emit anything, but when matter is falling into black holes, they are, that's what we call stratification, which emits X-rays, and we can see those X-rays. Okay. So we also have the 2 black holes although they cannot emit anything, but when they are rotating, when they are orbiting each other, they emit gravitational waves, which you can detect. Okay. Then we have the core of sun is opaque to light. I told you, but neutrinos escape directly from its nuclear reaction. Then we have charged particles accelerated in supernovae remnants are detected as cosmic rays. That we have dense clouds of gas and dust may block visible light, but can be observed in infrared or radio wavelengths. So thank you so much for paying attention to this lecture. So in my lecture, I'm gonna dive deeper into each of these cosmic messengers. Thank you very much, and put your question in the comment section.